Assalamu alaikum, everyone. Okay, so before I start the new chapter and move on to the questions of the chapter that were needed to be done, okay, I'm going to
Okay. Sundar will.
yes.
Yes, no, Sundus, carry on. I was just trying to mention that Sundus will repeat diffraction, and then we will do the end of chapter questions. If you guys have any question regarding this chapter 25, mechanical waves, then after her explanation, that would be a great time to ask. Otherwise, we will move on to the next chapter, which is chapter 26, light rays. Yes. Okay, Sundus.
Yeah, so I'm going to okay. So diffraction is basically when a wave bends or goes through some modification, some change after it passes through a slit or an opening. Okay, so if so the if you look at the figures in your book on page, let me see, um
Page 108.
yeah, page 108 and 109, so figure 25.8a and b, uh these ones, okay, so you can see that the waves
Yeah.
are bending. So uh why this happens is because if you look at the slit and imagine that this is the wave that is coming towards the slit and that is going to be modified by the opening in the slit, you can think of think of a bar tapping the surface of the water. So here we have water, and the bar is tapping the surface of the water at regular intervals. So the bar has this whole surface of contact. So I want you to think of every point as a source of radiating waves. Okay, so they're basically going to be radiating
As a
from,
source of circular waves, right?
yeah, as a source of circular waves. So there are waves moving in every direction, and so each of them are 1 point, so each point is going to give us circular waves. Okay, and then those circular waves proceed onwards in the form of a straight wave, and I showed you how, right, before. So once they reach near the slit, you can see there are going to be multiple points over here. So over here I have only drawn 4. So as these 4 points are going to progress through the slit, these two, so let me name them. This is A, B, C, and D. So B and C are going to proceed through the slit without any interruption. Okay, but A and D are going to get bent because there are many points here, right? So I'm going to draw 2 extra between each. Okay, and so the ones over here, the ones that are passing through the slit, so these are the ones that are passing through the slit, they are going to remain straight, because I mean they were passing, there was no interruption, right? But these ones had to kind of like wait. Think of them as people. Okay, so once these waves had passed, now they could just like turn and get into the slit too. Okay, so they came after B and C. So A and D come after B and C. So B and C have already proceeded ahead, but A and D have to catch up later. And when they're like catching up, they form this kind of curved shape, and which is what we call diffraction or modification. And this is how they, get bent. And the reason why they get bent more when you make the slit equal to their wavelength is because wavelength is kind of like smaller compared to the length of the whole bar. The whole bar is really big, and wavelength, if you remember, is the space between two troughs. So that's going to be the space here, right? Between two rays, that is going to be the wavelength, right? So um, you can see that the space is really small, and smaller the space is, less the particles that are going through are going uninterrupted, and more of the particles have to kind of like catch up, right? So there's more bending, more curving. And when the slit is open up really wide, um, more of the particles can go straight through, and there are few that bend at the edges. So you can see this happening at figure 25.8a. You can see that the slit is the size of the wavelength. Okay, so the wave length is from this to here, right? This, and it's really small, and so less particles are going uninterrupted, and there's a lot of bending going on. And over here in this figure, you can see that most of the wave particles are like going right through the slit uninterrupted, but and only the edges are getting bent. Okay, so do you guys have any questions about diffraction?
Yeah, this process of diffraction was already explained, but I asked her to repeat because of Shamim. Because Shamim asked in the group regarding this figure, why do the waves bend? So this was in response to that question. So even if she is not able to attend right now, maybe she can listen to the recording.
No, I think
Inshallah.
Shamim is here.
Yes, okay, good. Okay, so is there any question? Please feel free to ask from this chapter. And I think the yellow portion of this chapter is not included in the syllabus anymore. So all this interference and Huygens construction and everything is not included in IGCSE syllabus anymore. As far as I have checked in the recent syllabus. So these things are not included. So we will do the end of the chapter questions.
Yeah.
Should we move on, or is there any question?
If there's any query, you can raise
Okay,
your
so start doing the end of chapter questions and ask from the participants first if they want to answer. But please don't just give the answer. Also explain why. I mean, as well as you can. Okay, so page 111, questions.
So I'm doing question 1 first.
Okay.
Okay, so the lines in figure 25.16 are crests of straight ripples. A, what is the wavelength of the ripples? And the diagram is here. So they're asking you for the wavelength of the ripples.
So who wants to answer this question? So what is the wavelength of the ripple here? Yes, Nabil?
Miss, it's 1 centimeter.
Okay, yes, why? How?
As the total answer is 5 centimeter and there are total 5 of them.
No, there are 1, 2, 3, 4, 5, 6 of them, 6 crests. Okay, what are these lines? What are these lines representing? They are?
Crests.
Right, they are crests. Okay, and so the distance, so the space between two crests is?
One wavelength.
Yes, one wavelength, and the space between the two crests must be the trough, right?
Yeah.
Yes. So, okay, Nabil, yes? Yes? Can you unmute yourself? Yes? I'm asking you to unmute. Okay. Okay, I saw a few more hands raised. Hala, you want to explain why is it 5 centimeter? Why is the wavelength 5 centimeters? Oh, sorry. Oh.
I'll give you a hint. Basically, pay
The
attention. Okay, yeah.
Yes, yes, Hala. Yes.
there are five distances, like there are six wavelengths. There are six waves. There are six crests, but there are five
Waves. Yes, you are
Wavelength.
right.
waves.
So
So
they
we
are
divide the 5
crests.
by 5 and we get 1.
Very good. Yes, you are right. Yes, so there are 6 crests. Yes, Nabil. Nabil, I want you to pay attention. So there are 6 crests, but if you one wave is from one crest to another, right? One wave is from one crest to another. So if you count the spaces between these two lines, I mean, if you count the spaces between the lines, there are 5 spaces. Okay, first is between A and B, second is B and between B and C, third is between C and D, fourth is between D and E, and fifth is between E and F. Okay, so we have 5 complete waves divided. So we will divide 5 centimeters by 5 and we will get 1 centimeter. Okay, part B.
If 5 seconds ago ripple A occupied the position now occupied by ripple F, what is the frequency of the ripple? So I'm gonna repeat the question, and guys can now look at the
Okay,
diagram.
yeah, Sundus adjusted in such a way that the question and the diagram can be seen together at the same time. Yes. Yes. Okay.
Okay. I can label them here.
Okay, now ask. Yes, so who wants to answer this question? If 5 seconds ago ripple A occupied the position now occupied by ripple F, what is the frequency of the ripple? And keep in mind, wavelength is 1 centimeters. Wavelength is 1 centimeters. Okay, time passed is 5 seconds. Okay. Yes, Maruj.
The frequency would be 1, as just because it's saying that 5 seconds ago ripple A occupied the position of ripple F. Wait.
Yeah, so there are 5 waves, right? 5 wavelengths. So that means in 5 seconds, 5 waves passed by a particular point. Okay. If A is now occupying the position of F, that means in 5 seconds, 5 waves pass through the point F.
Yes.
Okay. 5 waves pass through the point F in 5 seconds. So what is frequency? What is the definition of frequency?
It's 1.
Who is this? Yes, Sarah. Yes, it is one. But without the unit, you answered without the unit, and you did not even explain. Yes, Sarah, please explain as well.
Because frequency is the number of complete waves generated
Per second, right? So okay, so in 5 seconds,
so
we
5 over 5 divided by 1.
5 divided by 1.
No, 5.
Yes.
5 over 5
Yes, 5 over 5, but
equals to 1.
yes, and what's the unit for frequency?
Hertz, H,
Yes.
and Z.
Yes, you are right. Okay, Sundar, can you please show us the working?
Okay.
Yes, can you please do the working properly with everything?
So So if in 5 seconds, so frequency is the number of waves passing through a point per second. So if in 5 seconds we had 5 waves passing through a point, right? In 1 second we're going to have, so I'm going to cross multiply and get 5 and then bring this down and we divide that and we get 1 hertz.
Yes, 5 seconds, 5 waves, and so yes, 1 hertz. Okay. Okay, part C. What is the speed of the ripples?
Now,
Yes, Sundar? Part C.
yeah, so who wants to answer?
Who wants to answer part C? You guys must have done these questions, right?
Sarah?
Okay.
Miss, the speed of the wave is equal to frequency multiplied by wavelength. So frequency is 1 and wavelength is 5. So we multiply 5 with 1 and the answer is 5.
So the answer is 5. Is the answer 5? No. No, Sarah, the answer is not 5. Yes, Hala? Yes.
We'll multiply frequency and wavelength. Frequency is 1, so is the wavelength, and we'll get 1 as the 1 meter per second as the speed.
Very good. Okay, and what will be the units for speed? 1
Meter per second.
meters? Is it meter?
Centimeters per second.
Very good. 1 centimeter per second. Please be careful about the units, okay? If your units are not correct, the answer, I mean, you will lose your marks. I mean, in our days, if units are not written, the whole question would be wrong. We would not be given any credit. Okay. Is there any other way to calculate the speed? Is there any other way for calculating the speed other than this, using this formula, velocity is frequency multiplied by?
Yes.
Yes. Tell me.
Distance over time.
Very good. Distance divided by time. So distance in this case is
Wavelength.
5 centimeters, right? From A to F, right?
Yes.
And that took how much time? So speed is distance over
5
divided
seconds.
by time.
Yeah.
5 seconds. So again, 5 centimeters divided by 5 seconds is 1 centimeters per second. Okay, let's move on to question number 2.
Okay. During the refraction of a wave, which two of the following properties change? The speed, the frequency, or the wavelength. So we have to choose 2 of the 3 of them. You can raise your
Yeah.
hand.
Come on. Yes. Abdul Ahad, you want to answer? Which 2 properties change during a refraction? I want new hands. Yes, Abdul Ahad? Yes, okay, Sarah.
Yes, it's the speed and the wavelength.
Okay, very good. What about the frequency?
Because the frequency is the number of waves generated per second. So the number of waves are the same, but the distance between the waves and the speed of the waves changes.
Okay, yes. Okay, Sundar, can you please explain them with the help of that analogy of people coming on a belt, on a moving belt? And so try to explain them, why does the wavelength decrease as the speed decreases? Why does the wavelength decrease during refraction when the wave enters from one medium to another?
Yeah. Okay, so think of all the waves as people, okay, and they're on a
Can you please,
conveyor.
with the help of a diagram?
Yeah,
With the
yeah.
help of a diagram.
Okay, so they're on a conveyor belt, okay, and actually those conveyor belts are like two conveyor belts, but there's no space between them. Okay, so this one's moving faster than this one. And you know
Write
what
down fast under that faster belt. Write down fast under the faster belt.
okay. Oh, sorry.
Yeah. And the other one is a slower. So think of the first belt as one medium and the slower belt as the other medium. Okay. And the people would be the waves.
Yeah,
Yeah,
and
just make lines for people. Just make lines for people.
yeah.
And
So
now people are standing with equal distances between them.
okay, so think of people as the waves, right? And so this is one medium, this is the other medium. So people step onto the fast conveyor belt with equal intervals. So I have one person here, and then this person moves here in a second, and another one steps up in his place. And you know that keeps happening, and so there are a couple people lined up. Okay, and then a time comes when this person has to face the slower conveyor belt, and so he's here and he's moving away slower. So in 1 second he reaches just here and the next person steps up, and in the next second he's here and the third person steps up, and you can see they're all getting like packed up really close together because no one is moving fast enough for the incoming rate of people. Did you get
Yeah,
it?
basically, yeah. So the thing is that the first belt is faster, so it is putting the people faster on the second belt. It is bringing the people faster towards the second belt. But because the second belt is slower, it is not taking the people away with the same speed. And so as a result, the people are getting, the distance between the people is decreasing, or the people are getting closer to each other. So that's exactly what happens with the waves. So if a wave is entering into a medium in which the speed is slower, the waves get closer to each other because they are coming at the same speed, which is, in from the previous medium, and it is faster. But because this new medium is, their speed is slower in the new medium, they cannot be taken away at the same speed. So they end up getting crammed up together. The distance between them decreases. So the wavelength decreases. Also appreciate the fact that the frequency will stay the same. Okay, whatever the frequency was of the wave in their particular medium, that will stay the same.
So like the
Okay.
same number of waves being generated, but they're closer together.
Yeah, same number of waves per second, but they are closer together.
Yeah.
Exactly. And the speed also, uh, no, the speed gets slower, right? So
Yeah.
during the refraction of a wave, which two of the following properties
The
change?
speed and the wavelength. The frequency
Yeah,
remains
but
the same.
doesn't the light get slower in the medium, and isn't that the reason why it bends?
Yeah, so it changes. The properties change. Speed changes and the
Oh,
wavelength.
okay. Yes. So sorry. Yes. So speed and wavelength change, and frequency is the only one. Okay. Okay. If there's any question, please feel free to ask. Okay. Move on to question number 3.
Okay. One side of a ripple tank A, B, C, and D is raised slightly, figure 25.17, and a ripple at P by a finger.
And a ripple at started at P by a finger.
Yeah. Okay.
And a ripple started at P by a finger. Okay. After 1 second.
After 1 second, the shape of the ripple is as shown. Why is it not circular? Here's the diagram.
Okay.
Um,
Why is it not circular? One side of a ripple tank ABCD is slightly raised. Okay. Okay. Who will tell? Why is it not circular? Have you guys done this? These questions before? Yes. Come on.
someone new. Do you want me to choose random people?
Yes, okay. Go ahead.
Okay. Maruj, you want to try?
Ajwa. Okay, who remembers? Where is this?
It is
Where
3A or 3B?
3A. We're on
we
3A.
we are 3A. We are doing 3A. Okay, in which
Can I
depth
try?
does yes, Nabil?
Speed, does speed depend on the depth, right?
Yes.
And
Yes, the
this is
speed,
the answer
yeah,
of
speed
this, right?
depends upon the depth, yes, and this whatever this is called, what is it called? One side, this ripple tank is raised slightly. The ripple tank is raised slightly. So, did you get a hint? The speed of the wave is affected by the depth, and this ripple tank is raised slightly. So, I'm giving you hints. Come on now. Fatima? Fatima? Yes, Fatima, you want to try? It's okay, even if you're wrong, it's okay. You muted yourself.
Hala?
Okay, Sundus, go ahead, you tell the answer.
Okay. So,
Have you guys, okay, have you guys done this in school, with school, these questions?
No.
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 No, but haven't you guys done this chapter in school?
Done it in
We
school,
did
not
this
the answer
chapter.
question.
Yes, sir, we did the chapter.
So you didn't do the questions at the end of the chapter.
No. No.
And have you completed the chapter? Have you moved on to the next chapter?
Yes,
Yes.
sir,
Yes.
in the afternoon, we are on chapter number 30.
So you moved on without doing the questions.
Yes.
Yes.
didn't you guys try it yourself?
Okay, it's okay. Sundus, go ahead and answer.
Okay. So basically, the hint is uh on the phrase raised slightly. So if one part of the tank is raised slightly, the waves on that part are not going to move too fast. They're going to be at a different speed than the rest of the waves, and that is why it's not circular. So the answer is because the depth of the tank is uneven, the waves are not circular. And
See, if you, yes, okay, go ahead.
so I was about to move on to question B. So if you
No. I think it needs more explanation. See, if you have a dish of water, okay, if you have a square dish of water and you raise one end slightly, I wish I could show you an actual dish with filled with water, and if I raise one edge slightly, but use your imagination. Imagine that I'm doing it in front of you. Then of course one end which is still lying on the ground will be deeper as compared to the end that I picked up. The end that I picked, because the water will move towards that side which is still on the ground, right? Because I am raising the other opposite side of the dish. The raised side of the dish will have less water because the water will flow towards the lower side which is still on the ground. So therefore the side which is still lying on the ground will have deeper water. Okay, that will have deeper water as compared to the side that I picked up that will have shallow water. Okay, and remember the waves are faster in deeper water. They're faster in deeper water, and therefore the wave will travel faster and farther. During the same time period, it would travel farther on the deeper end. So you can see the shape of the circle. Okay, let me, yes, Sarah?
Is that the reason why bubbles are always on the top?
No, bubbles being at the top doesn't have to do with waves. Bubbles are gases. And because gas is less dense than liquid water, it rises due to the difference in density. Okay,
Okay.
that's a different thing. Yes. Okay, so let me wait. Okay, wait. I'm trying to start my video. Yes. Yes, so you can see that the wave has traveled farther on this side. So this was the side which was lying on the ground. This is the other side which was raised. Okay, so because this was deeper, the wave traveled faster on the deeper side. Now they can also, right, this is part B. I was about to say that they can also ask this question, but they have already asked, which side of the tank has been raised? Now it's easy, right? This must be deeper. That's why the wave traveled farther on this side. This must be shallower. That's why the wave could not travel faster here. And so this side must be raised because the raised side is the shallower side. Did I make sense? Right? That's the question right at the end. AB.
Yeah.
Yeah, AB is the side raised. Ripples travel more slowly towards it. Therefore, water is shallower in this direction. Okay? Okay. Okay, then we have this. Okay, Sundus, go on. Question number 4.
Okay. So. Um, okay. Question 4. Okay. Figure 25.18 gives a full-scale representation of the water in a ripple tank 1 second after the vibrator was started. The colored lines represent crests. A, what is represented at A at this instant? So I'm just going to bring the book for the diagram. Who wants to answer? Akbar, Fatma, Marooj, Momina, you wanna try? Momina?
Sundus, go ahead and solve it.
Oh, okay. So
Okay.
they're asking. Did you have something to say?
No, wait. Yeah, okay. Look at this. Sidra brought for us this dish filled with water. Okay, so if I raise it, can you see the side which is raised, it has shallow water as compared to the side which is still on the ground. Can you see now this part is deeper, has the depth of water is greater as compared to the other end, right? So I was just trying to show this. Okay, move on, Sundar. So okay, so if these lines are crests, then what would be the region between the crests? This is so easy. Come on now, Hala.
Trough.
Yeah.
Very good. Who said that? Very good. Very good. Okay. Okay, mute yourself. Okay. Now move on. Estimate the wavelength. Estimate. That means in a ripple tank, 1 second after the vibrator was started. 1 second after the vibrator was started. The colored lines represent crests. Okay, estimate the wavelength. So within 1 second, how many waves did you have? 1, 2, 3, 4, 5, 6. 6 waves in 1 second. Okay. 6 waves in 1 second. So that should be the frequency, right?
Yeah.
Is the answer 6 to part 3? B part 3? Sundus, please check. Oh
No,
no,
it's 5.
it's 5. Oh, okay. Sorry. So I did the same mistake. There are 5 waves. One wave is between this crest and this crest. 1, 2, 3, 4, 5. Yes. So 5 waves in 1 second. Okay. So what would be the wavelength? Okay, Sundus? Or if there's anybody else who wants to volunteer. Okay, Sundus, go ahead. Gives a full scale representation. Full scale means what?
That means that we can like measure on the diagram.
Yes, full scale meaning that the diagram is representing the true length. Therefore, you can go ahead and measure. So, okay, Sundus, measure. You have a ruler?
Okay. Let me get one.
Measure the distance between the two crests. Or if you guys have ruler, please go ahead and measure and then let me know. I don't have a ruler with me. Come on, come on.
Miss, it is 3 millimeter, I think.
3 millimeters.
Yes. Okay, so 3 millimeters. So, okay, whenever you come across full scale, that means exactly as you measure. Please mute yourself. Okay, if they don't write full and they just say figure 25.18 gives, what's the word they use?
Not
They
to scale.
sorry?
Not to scale.
Not to scale would be just the opposite of this, but no, there's another term they use according to a scale, any scale. Okay, they won't mention. So what does that mean? That means that there is some scale that we don't know of, but you can still measure, but you can use it for your calculations, because the measurements that you will get by measuring would be proportional to the actual values. So you can use, you can use the measured values in calculations, but those will not be the actual measurements, but you can still use them for calculations, but they are like proportional to some ratio. Okay, but full scale meaning exactly as they are. And if they say not to scale, then that means you will not measure at all. No need to measure, because the diagram is not to scale. Okay. Okay, so wavelength is 3 millimeters. Frequency we found out was 5 hertz. Now speed. Okay, if we did not know the frequency, forget the frequency. And if we are going sequence wise from 1 to 3, how would you calculate the speed? Now you know 3 millimeters in. So the total distance that this wave traveled in 1 second was this outermost wave. What was the distance that it traveled in 1 second? Because this took 1 second, right? So it traveled 3 millimeters, 3 millimeters, 3 millimeters, 3 millimeters, 3 millimeters. 1, 2, 3, 4, 5, 3 fives are 15. 15 millimeters in 1 second. What's the speed? What's the answer?
It's 15 millimeters per second.
Yes. So see, so okay. Okay. So 15 millimeters. So so you got it, right? Okay, frequency, I told you frequency is calculate the number of, count the number of waves. 1, 2, 3, 4, 5 waves in 1 second. Okay, so that would be the
That'd be 5
frequency.
hertz.
Right. Now, part C. Sundar, sketch a suitable attachment which could have been vibrated up and down to produce this wave pattern.
So pay attention to the wave pattern. There are circular waves. So what
Yeah.
type of wave source do you need?
What type of wave source would you need for this? Okay, I'll give you a hint. Straight bar or a pointed ball, sort of. Yes, Hamza?
A pointed ball.
Yes, a pointed ball. Definitely not a bar. But if, for example, you have a straight bar only and you don't have a metal ball, you don't have a pointed source, then can you have these waves?
No.
Yes.
Yes.
Who said yes? Who said yes? Please explain how. So if you don't have a metal ball, you just have a straight bar, can you still have these circular waves? I heard yes. Come on. If you said yes, then you must be knowing the reason, right? Share with us.
We can use the corner of the bar as a point.
Wow. Good imagination, good thinking.
And
Well,
we
the
can
examiner, yes?
also attach the bar at right angles to the water surface.
Who was this, Sundus? What was
Yeah.
that you?
Yeah. That's it.
Sundus, do you know?
I mean, attach a bar like this, right? Like this.
Like what?
Like this. Like I'm my video.
Okay, you know what? Whatever ideas you're giving me, Hala and you, Sundus, you'll have to draw a diagram of whatever you're saying. So however you would keep a ruler that way, or the corner, or whatever you're saying.
So
Okay, you'll have to draw a diagram.
so in the exam, I can just make two balls the way I've made here.
No, my question is, you don't have metal balls. You only have a ruler. Now what? Now what? And you want circular waves. Now what?
You tap it with
Can
both.
still use the corner.
Nuh-uh.
We can tap it with the edge. You can show someone tapping the.
Well, yes, you can. Well, yes, you can use the edges. I mean, we cannot stop you from doing that. But
Oh yeah,
look
we
at
can
this.
also use a slit.
Thank you very much. Thank you. Yes, we can use a slit. Okay, the width of which would be equal to the wavelength, and then the straight waves can be converted into circular waves, like here. Yes, so if you have a bar, if you have a bar only, if you have a ruler, you can convert those straight, waves into circular waves by then using a board or something. But yes, provided you do have a board with a slit, and the width of the slit is the same as the wavelength. If it's not the same, then you will have to make the slit that big. I mean, you'll have to adjust the size of the slit. Okay. Then now question number 5.
Copy figure 25.19. Okay. Copy figure 25.19 and show on it what happens to the waves as they pass through the gap if the water is much shallower on the right side than on the left.
Okay. What happens to the waves as they pass through the gap if the water is much shallower on the right hand side than on the left?
So,
well, if it is, okay, Sundus, go ahead.
So we know that if it is shallower on one side, it's gonna move slower on that side, right? And also if it's passing through the slit, it's gonna get diffracted. So using these two pieces of information, I can make the waves bent, but also like closer to each other.
Yeah, but Sundus, keep the wavelength the same. Keep the distance between them.
Oh, but they're closer
Okay,
together.
okay. Oh yes, oh yes, oh yes. Good job, Sundus. Good. So, no, Sundus, you had to increase. You had to increase the distance. Yeah, you did just the opposite. You crammed them up together because you see, on the left-hand side, the water is deeper.
Yeah, so I mean, if they're
So
moving
they're
to the
gonna go
shallow,
faster. They're going to go faster, and if they go faster, the wavelength should increase.
oh, okay, so it's shallower here.
Yes, it's
Okay.
shallower on the right-hand side.
I'm so very sorry.
So take out a fresh piece of paper and draw a new diagram.
Okay.
Yes. Okay, so because the water is deeper on the left-hand side, so the waves are passing faster. And so because the water is taking the waves faster, the distance between them will be increasing. So wavelength would increase, but yes, they will also become circular. Okay? Okay. Is there any question? Is there any question? Any confusion? Okay, Sundus, let's move on to the next chapter. Okay, I did not check your SOS, your scheme of studies. I don't know what the next chapter is according to your scheme of studies. Nabil,
Light rays.
Light rays.
light rays?
Yes.
Okay,
Yes, Miss Light
Okay.
Rays.
okay, okay, Sundus.
Ibrahim, can you mute yourself?
Mute it kindly. Okay, Sundus, move on to the next chapter, please.
Okay. Okay.
So they're talking about the sources of light here.
Yeah, so first of all, they're talking about sources of light. So there are two kinds of objects, luminous and non-luminous.
Okay, another thing, light, just a recap, light is a part of dash. Tell me what will come in the dash.
The electromagnetic spectrum.
Very good, wonderful. Okay, so it's a visible part, right? The visible part with the 7 colors. Okay, so it does not require medium. Transverse waves travel in straight lines, right? Yes, okay, now Sundus, move on. Sources of light.
Okay,
We have to
so we have like two sources of light, luminous and non-luminous. Luminous sources of light produce light, and I'll tell you how in just a second. Non-luminous either absorb or reflect. So everything around you lights up when you turn on the bulb because it's absorbing the light and reflecting the rays of colors that you can see. So they're non-luminous, they're not producing any light, but they're absorbing and reflecting it. So the different ways in which sources of light can produce light is by using resistance wires and passing electrons to it. So light is primarily made of electrons. It's made when atoms get excited, and basically the electrons in the atoms get excited. So if we have like a bulb over here, and there's a current passing through it, and there's a resistance wire in the bulb, the electrons are coming in from this side, and they're going out from this side. So this wire is, as you can tell by the name, of high resistance. So it's very thin, okay, and all the electrons want to pass through it. So when they're passing through it, they kind of get really excited and crammed up. So they emit, the coil gets really hot and they get excited, and so they emit photons of light, and that's how you can see light. Okay.
Yeah, basically this filament is tungsten. Okay, it's a transition metal, and when a current flows through it, it offers resistance, and because of that resistance, heat is produced because electrons have to work against this resistance to be able to pass through the tungsten filament. and work done is equal to energy transfer. Remember from physics, work done is energy transfer. So when they work, their energy is transferred into thermal energy. Okay, their kinetic is converted into thermal energy. Now, if you remember the electromagnetic spectrum we discussed in our last physics class, the visible part is Vib-Goyer. Okay, so when we have light, we have all those colors together, and so all the colors together give us white light. And on one side of Vib-Goyer is infrared, on the other side was okay, so on one side was infrared, the other side had ultraviolet. Okay, I have turned my video on. So remember, thermal radiation or light, which is made up of these three. Okay, made up of these three. So the energy is increasing this way. Energy is increasing this way, and wavelength is increasing this way. Okay, so more the heat, more so you will, first of all, you will get infrared when the temperature is low, and as you increase the temperature, you will get red hot. Further, you increase the temperature, and can you also recall that all you will see all these colors in the flames of fire? So remember, the red part of the flame is the coolest part, and the white part, or the violet part, is the hottest. And if you increase the temperature even further, then there is ultraviolet radiation as well. So when the electricity is passing through this tungsten filament within the bulb, where is it? Oh, they have not shown. Okay. So when the thermal energy passes, or when the electricity passes through that tungsten filament, the thermal energy is released, and that thermal energy causes that filament to be white hot. And that white hot is in the form of visible white light. Okay, Sundar. Yes, Sundar?
Yeah. So okay, just
Yeah, so you were discussing luminous?
yeah. So I just had to fix the video. Okay, so so yeah, so light is part of what we can see, and it helps us see, right? So these photons are packages of energy which emit light. Okay, and so what actually happens is, like, it's the same phenomena as the aurora borealis. So basically, the particles have electrons which get excited. This is not exactly what happens in a current, because that's just electrons and not atoms, right? But it's kind of the same thing, because over here in aurora borealis we also see lights in the sky, and that's because ultraviolet radiations make the electrons excited, and so the electrons jump from their energy level to a higher energy level. And then when that radiation kind of goes on, okay, when they come back to their energy level, they're coming from higher to lower energy level, they release some energy, and that energy is released in the form of light, which we can see and we can also make use of. So so sometimes we can, Shamim, that was your question. You asked how lasers work. So basically, in lasers, we concentrate all of these excited particles and all of the energy from the electrons, all of them to one point. And the way we can do this is by using a tube which has mirrors on both sides. Okay, so we have all these particles, right? And then we have a battery. Okay, so we have a battery, so we have terminal endings here, and it's attached to a circuit. Okay, and the electricity electrifies the air, sort of, and one of the particles emit a photon. Okay, and that encourages other atoms to emit photons, and then all of them are emitting photons, and then you have mirrors on the side, so they get kind of like reflected back and forth, and so they're concentrated to one point that you can see the whole way. Some lasers you can see their path, some you cannot. Okay, and sometimes they're very strong enough, they can cut through, so all this energy is concentrated at one point, and you can use that to cut through metal plates. You can use them for scanners to read barcodes at library checkout, CD players, optical fibers, and you can also use them in surgeries because they get strong enough to kind of like cut the organs. This is only for like eye and ear surgeries. Printing, surveying, and range finding. You can range find by uh, like calculating the amount of distance this is reflecting back. Okay. So then we can come to rays and beams. So basically light travels in straight lines, okay, and when they travel away from one point, they're called diverging. And when they come to one point, they're called converging. And these are just parallel rays. Okay, so it's important to know this because there are different types of rays behave in different ways. So rays, beams, same thing. Okay, so over here, they are coming out, they're moving away from each other, so they are diverging, they're coming together at one point, so they're converging, and these are parallel, they're going straight through. Okay, and also if you look at the figure 26.3, you can look at the book for a clearer picture. You can also sometimes see the beams in at your window and even in the forest, because the particles in the air reflect all the sunlight. Okay, so when the sunlight falls on the dust particles, they reflect it, and you can kind of see how the light is traveling in straight lines. Okay, we also use the same phenomena for Brownian motion. And
Okay, so beam is a collection or a bundle of a lot of rays, right?
yeah,
Yes, and ray is just the direction of the path in which light is traveling. It's
yeah,
the direction, right?
yeah,
Okay, that we use in diagrams,
yeah,
right? So a laser gives a beam, right? A laser
yeah.
gives out a beam, right? Okay, so these are the three types of beams of light on page 113: parallel, diverging, and converging. Diverging, originating from a source, radiating out from a source, and converging is, coming on to one point. So laser has parallel, right?
Yeah.
Laser, the beam that is given out by a laser is made up of parallel. Is it?
Yeah, but there are also some really strong lasers which use converging.
Oh, okay. Okay, so it varies.
Yeah.
Okay. Okay.
So then we can, I'm gonna do the practical work on page 114, which is the pinhole camera.
Yeah, only 2 minutes are left. I don't think you'll be able to finish this. Only 2 minutes are left. So let's just stop here and ask. I could see Ibrahim's hand raised. Yes, Ibrahim?
I was asking that the magnifying glass have converging, diverging. What length? What type of lens?
Yeah. Okay. Ibrahim, we will do the magnifying lens when we will do the chapter of lenses. Okay. Then we will be in a better position to. And
yeah,
I think it's diverging, but I'm not sure at the moment.
and there's like a whole chapter on lenses, so don't worry.
Yes, there's a whole chapter on lenses, so we will deal with this because it involves refraction and everything. Okay. Okay, is there any other question? Okay, Sundus Sidra is asking that in laser, we are trying to bring the electrons to one point according to what you said. Is that what you said?
Yeah, yeah.
We are converging the electrons to one point?
Yeah, so some lasers keep it just parallel, so they're all traveling in one direction, like really close together. There's another law of coherence, which is kind of complicated, but some really strong lasers converge all the rays to one point.
So that means the beams that are emitted by lasers are converging.
Yeah, sometimes.
Yeah, but
Usually
not
it's parallel.
always.
Yeah,
Okay.
yeah.
Okay, is there any other question? Okay then. Okay then, thank you very much, Sundus, and everybody else who participated and for attending. Okay, assalamu alaikum wa rahmatullahi
Okay,
wa
Miss.
barakatuh.
Allah Hafiz.
Allah
Allah
Hafiz.
Hafiz.
But